Experiments in Physics with Dr. Frank Oppenheimer was produced in cooperation with University of Colorado Television. Experiments in Physics with Dr. Frank Oppenheimer. A brief demonstration of the equipment used in the Library of Experiments in Physics, produced in cooperation with University of Colorado Television. Today's experiment
This experiment, one can study what happens when two vibrations, one, say, moving up and down and the other horizontally, are imposed on an object, and look at the patterns that result of this composition of the two perpendicular vibrations. The vibrations are produced by this audio oscillator, which feeds into the back of this device here, which splits the output into two outputs, one which can go to the horizontal, that is this one here, and the other which can go to the vertical, that is this here. These vibrations are, of course, imposed on the electron beam of the oscilloscope. That is, if I unplug both of them, I can see just the spot. If I put in the one that goes to the horizontal, I get a horizontal vibration. If I put in the one that goes to the vertical, I get a vertical vibration. If I put in both of them, I get a combination. But one can't see what the relative amplitudes are directly from this scope of these two vibrations, and one can't see what their phases are. So both these vibrations are also displayed on this scope so that one can measure the relative phases. Let me disconnect this again. There's the vertical one, which shows just there. That's the one that's doing the triggering of this scope. There's the horizontal one, and you notice it's unsteady because it's not properly triggered, but you can see that here's the horizontal, and there's... that is essentially all that one is involved here. This device, when I turn this knob, change the relative phases. Notice how they move with respect to each other. This changes the relative amplitudes of the two vibrations. And so one can study how this pattern changes with both amplitude and phase. But because of the versatilities of the oscilloscopes, one has to make some initial adjustments. The amplitude that's displayed here depends not just on the input amplitude, but on the way these amplifiers are all set. And so the simplest thing is to say, let's start out with the amplitudes equal and the two signals in phase. That means with this knob turned all the way down, and since I want to vary it with this one somewhere in the middle of its total range. In order to then have the amplitudes equal here, I have to adjust these. And given a certain deflection here, and in fact on this scope, you don't want to use more than two of the large squares because it's not a very linear scope, and if you let the beam go out to the edges, you'll get distortions. The overall height is determined for both directions by this. So if I set that there, then if I move the vertical gain, if I increase the vertical gain, I'll get too much vertical oscillation. If I decrease it, I'll get too little. So I'll set this initially so that I get a horizontal line, say, just filling this first square. I mean a 45-degree line, not a horizontal line. And to do that, I'll get it centered. I can change the vertical centering, and I can change the horizontal centering with these two knobs. And if it goes right through the center of that square, let's see, it takes a little fussing around to do that. And I still have it tipped a little too much vertical. I'll cut that down a little bit. It goes through the center, it goes through that corner, it goes through that corner. Of course, I have to look straight in to be sure. And now I have the 45-degree line. That represents equal amplitudes. So now I'll adjust these. to show that they're equal. I can change their position. I'll put one on top of the other, and notice that they're not quite the same height. One is a little bigger than the other. So I'll increase that one a little bit and readjust the position each time, and see if I can get one just put on top of each other. And now they're not quite, but almost exactly the same height. So these are set for the same height. This is set at 45 degrees, and I won't change those adjustments again as long as I do the... This selector is set at chop to show both traces. This central one here is set at the normal position. If it's in the wrong place, it inverts the phase of one of them, and notice that they seem out of phase now because this says inverted, but actually they're in phase. So I want to be sure that's at normal. The time base, I just put at any convenient thing. If it's hard to measure phases if they're too short. I don't see a full wave if it's too long. In fact, it's nice to adjust that so that they're exactly 4 divisions to a wavelength. Then if I move, I can measure the phase in units of 1 division, which would be 90 degrees. This is set at about 1,000 cycles as a convenient. Having gotten that set and not touching these adjustments anymore, I can now work entirely with this. If I change the phase, I can measure the phase change here, and I can describe the pattern that happens there. If I change the amplitude at any time, I can measure the amplitude on here and draw the pattern as the amplitude just for a given phase. And notice that I can get rather complicated changes, and part of the experiment is to study that. If I go clearly all the way to 100 here, these don't quite come to 180 degrees. That because at this frequency, or at any frequency, I can't quite get the range here, but I can put in a different capacitor in the phase change network by flipping the switch from C1, which is backward, to C2, which is forward, and notice that makes that jump over that last little bit, and I get my 180 degree phase change. So this then is the experiment. Notice that as I change the phase, the relative amplitudes change a little bit. Of course, even when this is in the C1 position, and if I want to see what happens at equal amplitudes, I will have to adjust the amplitude for each phase so that they're equal. This is fairly simple, but to understand it and to do it over and often enough so that you can see what's really going on will take you a considerable amount of time. Having done this with the same frequency on the X and on the Y, you may be interested in trying different frequencies, and rather than use 2 audio oscillators, which you could do, you could also very simply just get the 60 cycle from this scope here and turn this down from 1,000 to 60 cycles and set the corresponding sweep rate here. So there I have 60 cycles, but now I will disconnect it from this side. This is the one whose phase is variable, and connect it to this calibration output. And notice now I have 2 sine waves on here, and the phase is obviously changing continuously. If I adjust this, I can make the phase stay as nearly constant as I want to. And you notice that there's little distortion. This isn't quite as nice a sine wave as the audio oscillator, but it goes through the patterns that it was going through a moment ago. But now I can change this so that the horizontal still has the 60 cycle on it, but the vertical will have maybe twice that. And I can again get patterns which I can make stay as nearly stationary as I wish to by adjusting this. And again, I can change the, well, I guess I can't, the relative amplitude at this point. I can change the relative amplitude by changing the audio oscillator. And I can go up to 100 other multiples of 60 cycles and look at these Lissajous figures, always measuring the relative amplitudes and the relative phases, and try and understand what's happening with these various pictures, which is quite fascinating as well as instructive. I think that these are the main things that you have to get used to. But having seen these pictures, I think you can reproduce them even though it seems a little mysterious. That's all that's involved in this experiment.